可以了吗 ？Okay, yeah. Sorry, I mean it takes a little bit longer. I actually went to the department office for some issues. Okay, so I already explained like how you can set up the rope. Okay, in the visualize like a diagram. Okay, and you can also set a reference value. Okay, in your posterior distribution. Okay, just need to, when you use a plot posterior, just set a ref VAL, okay, to be, in this case, 0.5, and it looks like this. Okay, not only it will tell you, okay, it will mark this particular point. It will also tell you, okay, how much percentage of the data is below this point and how much percentage of data is above this point. Okay, so this gives you a lot of information, on this reference value. Okay, so okay, then we can talk about these loss functions. Okay, the loss function is it's kind of, but not exactly, like the loss function that we use in like deep learning. Okay, in the deep learning, we train the model based on a particular loss function. Okay, but for Bayesian analysis, it's slightly different. Okay, because there's no training involved. Okay, the only thing that's like happen in Bayesian data analysis is like a sampling process. Okay, you are generating a lot of samples from a particular from some distribution. Okay, so make a good decision. It's important to have the highest possible level of precision for estimating the value, okay, of the relevant parameters. Okay, but it's also important to take into account the cost of making a mistake. Okay, so the cost or benefit trade-off but can be formalized by a loss function. Okay, so this loss function sometimes is also called a cost function, objective function, fitness function, or utility function. Whatever you call it. Okay, actually, it's almost, these names are almost identical to the names used in deep learning, but I just have to remind you, okay, they are different. Okay, their purpose are similar, but the usage of this function is very different. Okay, so the key idea is to use a function which capture how different the true value and the estimated value of the parameters are. Okay, so larger the value of the loss function, obviously the worse the estimated result is. Okay, so for example, okay, there are like some example of the loss functions. For example, like quadratic loss, okay, or like absolute loss, okay, or 0-1 loss. Okay, quadratic loss is like normally we get that and divide it by a number of samples. Absolute loss is also we get that the summation of the absolute loss and divided by number of samples. And the 0-1 loss we just get like the number of like samples that are different from in which like the prediction is different from the data. Okay, so that's like the indicator function, highest indicator function. Okay, so practice, we generally do not have the value of the true parameter theta at hand. We normally do not have that because the theta we have is just a posterior distribution, not a real value. Okay, So we can we have estimation in the form of posterior distribution, as I said. So what we can do is to find out the value of theta hat that minimize the expected loss function. So this is like we will transform this into to minimize expected loss function. Okay, find the value of theta hat to minimize the expected loss function. So by expected loss function, okay, we mean the loss function averaged over the whole posterior distribution. Okay. So for example, here, okay, in this code, okay, we have two loss functions, the absolute loss and the quadratic loss, okay, and we will see here we use sampling, okay, grid approach, okay, we divide the region into 200 points, and we then plot the curves accordingly, and we will include the value of theta hat that minimize each loss function. I think this is fairly easy. Loss f underscore a represent the absolute loss function. The loss fb, okay, represent quadratic loss function, and the computation should be fairly simple, okay. In Python programming, and when you plot it, okay, it looks like this. So you can see that different loss function will have the different theta hat at the minimum place. Okay, you can see obviously for I think loss A, the absolute loss function. Okay, the theta hat that minimize the absolute loss function is at 0.32, and the theta hat that minimize the quadratic loss function is at 0.33. So they are slightly different, and interestingly, you will see that, okay, the first value is the median of the posterior, and the second value is the mean of the posterior. Okay, so if you consider this, minimal, the expected, expected loss function. Okay, the value that minimizes the expected loss function. Okay, for quadratic form, it's like a mean. For the absolute value case, it's the mode. Okay, this is not a formal proof. You can verify this by computing mean. Okay, the theta post. Theta post is like the posterior distribution of the theta. And if you compute it, it will give you the NP dot mean will compute the mean and give you that mean, and the NP dot median will give you the median of the posterior theta posterior distribution, and you can verify what I have just said, by using these two function calls. And obviously, this is not a formal proof. Okay, take-home message is, different loss functions are related to different point estimates. Okay, one possible question I can ask you is, can you prove? Okay, when you want to minimize, for example, this quadratic loss function, the result is is a mean of the posterior. Okay, can you prove that? Okay, and also the value that minimize the absolute absolute value loss function is a median. Okay, can you prove this? Okay, I may give you questions like that in your homework. Okay, This is like a little bit more mathematics, but you know, you can try to check out if you can do it. So, having said that, okay, we talk about like those two different loss functions as example. So I mean, should we explicitly choose a loss function? Okay, if we want to be formal and we want to compute a single point estimate, okay, then we must decide which loss function we want. Okay, so if we want the single point estimate, I mean, we must decide loss function. Okay, the opposite is also true. Okay, so if we choose a given point estimate, okay, we implicitly deciding a loss function already. Okay, so these two things, I mean, you know, are correlated anyway. Okay, so the advantage of explicitly choosing a loss function is that we can tailor the function to the problem. Okay, so not just like using the predefined like a rule, okay, which may not be suitable for our case. Okay, so for example, in many problems, the cost of making decision is asymmetric. What do you mean by symmetric? Okay, it's not the same to decide whether it is safe or not to administrate a vaccine to children, okay, under maybe age of 5, and being right, that being wrong. Okay, so if you consider this one to be right, and to consider this decision problem to be wrong, I mean, they are a problem of two sides, right? So if it's symmetric, that means like okay, the loss function, okay, should be able to be used. Okay, if this is loss function for one, the other loss function should be the opposite, because they are symmetric, right? But you know, sometimes we will find such a problem is not symmetric. Okay, so because this is so important, making a bad decision could cost thousands of lives, produce a health crisis. Okay, I mean, for example, like you know, the COVID-19 vaccination situation in Taiwan. I mean, now I think we are okay, but I wouldn't say we are very good in terms of vaccination, because I have quite a few relatives who don't do vaccination very well, and because they are, you know, I couldn't convince them to do that. I mean, unfortunately, I mean, so in Taiwan there are still people, I mean, suspect like vaccination. I mean, so that's like an important decision, obviously. Okay, so that could have been avoided by administrating a cheap and a safe vaccination, obviously. So if the problem demands, I mean, the problem is, demands a symmetric decision, then we can construct a symmetric loss function. Okay, in other words, like two sides will have a different loss function. Okay, so it's also important to notice, as the posterior is in the form of numerical samples, because remember we do this by using the grids. Okay, so we can compute complex loss functions that do not need to be restricted by mathematical convenience. Okay, or just for the simplicity. Okay, so because you can see we actually draw this by, you can see here, here. We generate like a 200 grid points in a range of 0 and 1, and then we do that. So it's actually very simple, okay, very simple. You can use a very complicated loss function. That's not the issue. Okay? So in practice, it's not true that every time people use a point estimate, they are truly think in terms of loss functions, okay? Because, I mean, normally we don't consider loss function. We consider like point estimate. We just consider like some point estimate are very common in scientific fields. For example, people usually choose maybe median just because it is more robust to outliers, or use mean just because it's simple and familiar concept, okay? Or they think that their observed data is truly the average of some process. Okay, that's it. Okay, so it's like when we consider point loss, I mean, we normally do not. A lot of time we do not consider the associated loss function, okay, behind our decision, okay. But I just want to point out that, okay, when you have a point estimate, okay, you implicitly choose a loss function behind your decision, okay. So then, well, we are moving to the Gaussian model, okay. We previously talked about the concept of Bayesian inference by using a beta binomial model, okay. And the beta binomial model is, used for explanation of Bayesian inference. It's just because this model is very simple, easy to understand, and it happens to have conjugate prior that we can show, like not only like a grid approach, but also conjugate prior. Okay, but there's another simple model that we can consider. Okay, obviously is the Gaussian, or what we call normal model. Okay, and if you still remember, I mean, we actually talked about Gaussian model or normal model earlier. I mean, when we talk about conjugate prior, because I told you, obviously, beta prior is a conjugate prior for binomial likelihood. But for Gaussian likelihood, okay, you can also use Gaussian prior. Okay, so and the Gaussian, okay, I mean, you can also use Gaussian prior because Gaussian prior is also the conjugate prior. Okay, by the way, so Gaussian are very appealing, okay, from mathematical point of view because, okay, because of its simplicity. Okay, first the conjugate prior of Gaussian is Gaussian itself. Okay, so that's the first benefit of that. Second, many phenomena, okay, can be approximated using Gaussian. Okay, especially when there are many factors that affect this phenomenon. Okay, so for example, like every time we measure the average of something using big enough sample size, then that average will be distributed as a Gaussian. Okay, so there's like a mathematical proof of this called like central limit theorem, okay, CLT, which is very famous in statistics. Okay, you can check out the Wikipedia page of the central limit theorem, okay, to see like when this is true and when this is not true, okay, so or when it is more or less true, obviously. So basically, like let me give you some example. Okay, for example, okay, the height of a person. Okay. By the way, like if you remember in the previous chapter, we talked about the height of like a number of American women. Remember? Okay. So if you look at the distribution, that distribution is a nice bell shape, right? And we use that to describe like a Gaussian distribution, if you still remember. And another example we use is the height of the door, which was manufactured like at 7 feet tall. Remember? I mean, even, of course, that one, I mean, the distribution is much narrow. Okay, it's much narrower, much concentrate at central region. But I mean, when you look at that example, like closely, it is also bear shape. It is also like a Gaussian distribution. Okay, so it's because the height, okay, is like determined by a lot of different factors, okay, such as trait of the environmental factors. I mean, if you are eating well, like when you are a kid, okay, and many genetic factors, okay, how tall your parents are, okay, so we get a nice Gaussian distribution for the height of adult people. Actually, if you look at any observation, like which are affected by many factors, as long as you collect a large enough like a data set, normally it's like it looks like a Gaussian. Okay, so in summary, Gaussians are easy to work with, and they are more or less abundant in nature. Okay, so hence many of the statistical methods, okay, that we already know or have at least heard of are based on normality assumption. Okay, so it's important to learn how to build these models, and then it's also equally important to learn how to relax the normality assumptions. Okay, I don't think we can talk about how to relax normality assumptions this time, but next week we'll be able to talk about this. Okay, so something surprisingly easy. Okay, in Bayesian framework, I mean, to relax certain assumptions, I mean, in the modeling is very easy. Okay, with modern computational tool, okay, such as PyMC3. So let's consider one example that we will use the Gaussian model. Okay, this is called nuclear magnetic resonance. Okay, resonance. I mean, NMR. This is a technique that is used to study molecules and such as human or yeast. Okay, yeast is like I don't know another term to describe that. In Chinese, 酵母. I mean, 以后健健美啊，或养乐多，Yakult. Do you know Yakult? Okay, that type of drink. Okay, there are like certain living stuff like in that drink, right? It tastes good, and if you drink a lot, I don't think it's good for your health. But if you drink reasonable amount every day, I think that's good for health. I mean, so that type of drink contains yeast. Okay, so NMR allows you to measure different kinds of observable quantities that are related to unobservable and interesting molecular properties. Okay, so one of these observables is known as chemical shift. Okay, so we can not only get the chemical shift for the nuclei of certain type of atoms. Okay, and all of this is in the domain of quantum chemistry. Okay, and the details are irrelevant for this class. Remember, for Bayesian data analysis, I mean, a lot of people familiar or like a master in the Bayesian data analysis are people in respective research domains, such as in medical domain or in social science domain, or take this author as an example, his field is actually in quantum chemistry, so that's why he came up with this example. Okay, I'm not saying this is important consideration, because you can sort of like disregard like the problem. It's just consider, okay, the data set that he collected, okay. So this chemical shift, okay, we call that shift because we measured a signal shift from a reference value. So, and chemical, because the shift is related somehow to the chemical environment on the nuclei that we are measuring. But, you know, as I said, don't worry about this if you don't understand this topic too well. I mean, I don't understand this topic, myself either, okay? So you just treat it as like as a data set that we collected from somewhere, okay? So the choice of this example is based on author's expertise. I mean, he's into like quantum chemistry, okay? So for all we care at the moment, we could just have been measured the height of a group of people, the average time to travel back home, the weight of bags of oranges, or even a discrete value like a number of sexual partners of the tokay gecko. You know gecko, right? A type of, you know, like kind of like lizard or something. Okay, okay. So I mean, basically all these are, you can treat them kind of like a approximation of like a Gaussian. You can approximate them by the Gaussian distribution anyway. I mean, the last one is, you may argue, well, Gaussian distribution is continuous. How come there's a number of sexual partners of the gecko? I mean, obviously it's discrete, right? But if you can approximate the number, the integer, okay, by a continuous variable, then you can even, you know, model that discrete like a case by Gaussian distribution, okay? So keep in mind that we do not need our data to be truly Gaussian, okay? We just need, we only demand that a Gaussian is reasonable approximation, okay? So, you know, to our data. So for this example, we have 48 chemical shift values that we can load into NumPy array and plot by this following code. So we first get this data from here. Okay. Oh, by the way, this book, okay, that I use for the text as a textbook, okay, its code and its like data set are freely available. I mean, online. Okay. So take this one as an example. This is like a data set like provided by the author. Obviously, this is not like available outside. Okay, so you can search this textbook and search like where you can download the program as well as the data set of this textbook. Okay, and use it for your own purpose. Okay, for your own learning. Okay, and then. Okay, you can use Arvi's plot KDE to plot this data. Okay, and it will look like this. Again, this is kernel function, and the lower part indicate like the value of this 48 samples. Okay, and obviously you can see. This area, the samples are more concentrated in this area, right? And there's like there are two samples that are not in this range, in that range. These two samples are not in that range, right? Okay, so but you can see the majority of the samples are in this range. Okay. So, so this shape is looks like it's Gaussian enough, right? It's Gaussian enough. I mean, it looks like a bell shape. Of course, we have some outliers. I mean, two outliers out there, but I mean, well, it's you know, not too far away from Gaussian. So, you know, so we can model this. Okay, let's forget about the two outliers for a moment. Okay, and we assume the Gaussian distribution is a proper description of the data. We do not know the mean standard deviation. Remember, the Gaussian distribution has two parameters. One is mean, one is standard deviation, right? So for mean, okay, we don't know what the mean is. Okay, we don't know what the standard deviation is. Okay, but we can still model them. Okay, the mean, we can model this mean can be drawn from a uniform distribution with this LH represent the lower and the upper range of this standard deviation, of this uniform distribution. Okay, and this sigma, the standard deviation, is also a value that we draw from this positive normal distribution. Okay, the positive normal distribution is just like because, well, it's a average at 0, and with standard deviation sigma sub sigma. Okay, eventually this LH and the sigma sub sigma will be given. Okay, based on our experience. These two are considered prior. And once we have them, this is our likelihood. Okay? Remember, like, the idea, okay? If we don't know a parameter, we put a prior to it. Okay? So we don't know the mu, we don't know the sigma. So we put the prior to them. Okay? So one, it's a positive normal. I think the positive normal is fairly simple to understand. And why we use positive normal to model the distribution of the of the standard deviation value? It's because standard deviation has to be positive, right? It has to be positive. You cannot have a negative standard deviation, right? Standard deviation is a square root of something, right? So it has to be positive. Okay, so in the Krusk style diagram, it looks like this. This is called like a half normal. Okay, this is called half normal. Okay? So we get the mu from this uniform distribution. We get the sigma from this half normal. And this is the data we sampled. This is distribution we sampled the data from, okay, which is normal distribution. And when we convert this into like a PyMC3 program, okay, it looks like this. Again, it's so simple, okay? And here we set the L to be 40, H to be 75, which is large enough to include all the values in the data set, okay? Which should be enough. But if you don't know, we can set L to be 0, H to be 100 if you want. Okay, you can even further relax it. Okay, so again, this prior choice is determined by your prior knowledge about this problem. So of course, like the author is in this research domain, so he think like using 4075, okay, that accounts for all the data value, all the values. I mean, in the data set should be enough. So you can see we said, okay, lower equal to 40, upper equal to 70. Okay, this is uniform, PM dot uniform. Okay, and we get this mu from here. Okay, and we use the sigma, is drawn from this half normal, okay, with standard deviation 10. Again, why do we use 10 as here is based on the author's research background, okay. Just a large value. This is already pretty large value, okay, for the data, okay. If you don't know a good value, of course, you can even set this value to be even larger, okay. To make it like a not restricted to a certain smaller range, okay. So you set this here, sorry, okay, SD equal to 10, and then with the mu and the sigma, okay, then you specify mu and the standard deviation sigma. Observable equal to data. The data is you receive, you load it from a particular file here, right? Where? Here. Okay, and then, okay, you try to hit the inference button. Okay, again, you tried 1,000 samples. And you put the result to trace G, and then you use a plot trace to plot the result, okay? And when you plot this trace G result, you will find that it will give you two sets of the figures, okay? Why? It is because, remember, we have two parameters, okay? In this example, we have two parameters. One is mu, one is sigma. Okay? So, actually, okay, for this particular example, the result is really three-dimensional, okay, with x and y being mu and the sigma, and the data point being the third, the value of y to be the third dimension. Okay, but for like plot trace function, it will just plot this two-dimensional result. Actually, you can see that these two are marginal probability distribution for mu and the sigma. If you want to see the joint probability distribution, okay, you can use plot joint, okay, and feed in the trace G, and then it is going to give you the joint probability like this. Well, it looks like well, sorry, I don't know English term for that, but like some map will give you this, right? To show a mountain like this, 等高线图, okay? Because it's three-dimensional. The plot joint, okay, basically allows you to see the result from above. Okay, with different color will indicate like a different height. Okay, and the x-axis here indicate the value of mu. The y-axis indicate the value of sigma. Okay, something like that. It's three-dimensional, but well, that's the best it can do. Okay. So, well, and you can also output a summary of the trace, such as mean standard deviation and 94% HPD for mu and sigma, okay, from the trace G, okay. So, well, it's actually, well, because I have to go to a meeting like at 12 o'clock, so I think I have to stop here. So I will try to finish this example next time, okay? In the following, we are going to try to use posterior predictive check to see if this result is plausible, okay, is valid or not. But sorry, because I'm running out of time. So we will talk about this next time, okay? Yeah, so I'll see you next week. And remember, I will assign the homework 2 and put it on the E class, like before our next class, okay? See you next week.